Hello everyone, my name is Anurag Gupta. I'm from codeItDown. So what we have started in this week, we have already started with the heap data structure. So what we are going to learn today. First, tell me how many of you have means gone through the videos uh, and how many of you have tried solving that questions that we have already provided to you. Means, is there anyone who is having any doubt in the heap data structure? In the last session, we have discussed about the implementation of heap data structure with the help of array. Do anybody is having any doubt regarding that? If you are having any doubt, please tell. Is everything fine? Can we move further? I'm waiting for your responses again. Okay, Smith is saying no doubt. That's good. So what we are going to learn today, in the last session, we have discussed about the implementation of heap data structure with the help of array. But we all know that heap is a kind of binary tree, a complete binary tree. So always we implement tree using linked list. So what I'm going to do today, I'm going to implement today heap data structure with the help of linked list. So the concepts of insertion and deletion would be same, but I'm going to do it using linked list. So let me quickly revise the concept of insertion and deletion. So what I'm going to do, I hope all of you understand what a heap data structure is. Let's say I'm talking about a max heap, and there is a data, let's say 10 is here, another node to, I'm calling it today node because I'm going to implement using node today. Okay, sorry, it cannot be 20 because we are trying to create a max heap. So the root node will be always the maximum value. Let's say it is 8 and 9. Okay, it, let's say it's 5, 4, 3. Let's say this is our max heap. Every parent node is having the maximum greater value than its child. So what I'm going to do today, so in the last session what we have discussed, so we are implements we are storing the values in the array. So it was index 0, index 1, index 2, index 3, index 4, and index 5. Okay, but what we are going to do today, we are not going to store the values in the array because we are creating a tree type data structure. So we are going to use linked list for it. Let's say what the type of node will be. Let's say this node, there will be node, and this will have a data part 10. Let's say this will store in this part, the stored value will be 10, and a left child part and a right child part, as well as, let's say I'm storing the parent of the node as well. So the node will be of type, let's say instead of writing 10, I'm writing D means data. Okay, so how a node will be look like, a single node will look like something this. A data part will be there, a left pointer, it will have a address of left child, and in this part it will have the address of right child. In this part it will have the address of parent node, its parent node. Let's say this time 10 is there. In the data part 10 will be stored, and its left part address of 8 will be stored, and its right part address of 9 will be stored. So in its parent part, although 10 is our root node, so this is the root of our tree. It could not have any parents, so in the parent part it will have the data null. Okay, and again in this part as well, let's say in its data part 8 will be there. Let's say 8 is there. In its left child part, the address of 5 will be stored. In its right child, address of 4 will be stored. So Shrey is saying, I learned once that dynamic list implementation is used when we are unaware of size, number of nodes in heap as the size of array has to fix. But in CPP, as we have vectors, is there any other advantage of using linked list over array? So if you are talking about the particular linked list, not in the heap data structure, so yes, there would be there is lot of advantages of using linked list. Means in some cases that in the time complexity in the linked list is better than array. And if you're talking about the heap, yes, in the heap we cannot say that linked list has the best means better time complexity. So if you're talking about other parts, so yes, linked list has the linked list have the means better means some advantages, and as well as on the other side, arrays also have the some advantages over. You're talking about the heap only. So in the heap, because yes, you can use linked list means okay, I'll search first. Means is there any other advantages of means other than the dynamic size? I also don't know means is there any other advantage of using this? But we usually learn this linked list representation. Why? Because we generally use when we design our tree, we generally use linked list detection, linked list data structure. So to understand that, so in the heap as well, we do it with the linked list as well. Okay. You are saying searching is faster in array method. Yes, absolutely, searching is faster. Implementation become very easy with the help of that formulas. Yes, it becomes easy. But as a programmer, we also should know means how can we implement it using linked lists, because we have already discussed that part. So first let's discuss how the implementation of linked list look like, how that means processes will be there. After that we'll discuss means what are the advantages of using array and what are the advantages of using linked list. Okay. As the accessing of elements in the array implementation become very easy, and with the help of that formulas, yes, it becomes easy. So first let's discuss the means the concept how we can use linked list, because I'm why I have means made this session on the linked list, because in the next weeks we are going to implement trees. So in that we'll definitely going to use because in the heaps it is a complete tree. So using means array is fine here, but in the BSTs and in the binary trees, there if you are using means if you are using arrays, you'll be wasting a lot of memory, lots of memories in that. We'll discuss in that in coming sessions. Okay. So what I was talking about, let's say the node is there, and the first part will be having the data, and the second part, it's let's say it's storing the address of 5, and the second let's say in the right part it will have the address of 4, as well as one more part will be there, the parent part. In the parent part it will have the address of 10 stored. Okay. As well as for the 9 as well. So in the data part 9 will be stored. In the left part, the address of 3 will be stored, but in the right part, it because it is not having any right value, so in the right part it will have a null pointer. It will have a null value. Okay. And in the parent part it will have the address of 10. Is that clear now? How we are going to implement using linked list. Okay. So what I'm going to do, I'm going to code it. Let's discuss the insertion and deletion concept once again, in a very quick manner. Let's see what we're doing in the case of insertion. Those who are not there in the session when we are discussing it using array, let's quickly discuss it. And if you are still not able to get you can watch that video. We have discussed in that as well. So what I'm going to do, let's say I want to add 20 here. So what I'm going to do, I'm going to create a node, and I'm going to add it at the last. Okay. And because it is our last node, its left as well as its right will be pointing to null, and its parent part will be pointing to now 9, because this is our this is the parent of this new node. Okay. So now what I'm going to do, I'm going to call up Heapify function. What up Heapify function do, it compares the data that is being passed to its parent. If the parent is less than this value, it is going to swap both values. So 9 will come here, 20 will come here. Again, it will call a Heapify function passing this node as an argument. And what it is going to do, it is again going to check whether the parent of this node is having the greater value, means is having the value that is greater than this node, or it is less than this node. If the value at the parent is greater than this node, this is not going to do anything. If it is less than the child node, so it is going to again swap both values. So 20 will come here, and the 10 will come here, and 9 goes here. Okay, so we are going to swap the values only, not the node. We are not going to swap the node. If we are going to if we try to swap the nodes, the lots, we have to change the lots of pointers. So we are going to swap the values only. Okay, is that clear now? The concept of insertion. Can we move, or do anybody is having any doubt? Okay. So I'm going to code it. Let's say I'm going to make a class of, let's name it node or heap node. Let's say I'm naming it heap node. Okay, and what are the data members it will have? Let's make it all public so that we can use it on in our heap class. So what I'm going to do, I'm going to create a data in data, as well as I'm going to create, okay, it will not be a star because it's the name of our class only. Heap node, the first will be it's a left pointer, let's say. The second will be a right pointer, and the third will be a parent. Okay, let's quickly design our constructor for it, because when we use class representation, we always use a constructor. So what I'm going to pass through this constructor, let's say I'm passing a value. So what I'm asking my constructor to do, let's say store val into data part, and the left pointer store null, because in the starting when I'm creating a node, what this constructor needs to do, it should just create a node, and it should store the value in the data part, and the left, right, and the parent should be in the starting, it should be null. Okay, okay, let's come to our class representation. So what I'm going to do here, let's say I'm going to create our class. Name of this class will be heap. So what I'm going to do, the first data member of this class will be the heap node. Let's say it will be a type of pointer, and I'm naming it root, because this will be our root of that tree. Okay, let's say I'm making a public constructor for it. So what this constructor is going to do, let's write our constructor for it. So what it is going to do, it is going to, in the initial part, our root will be pointing to a null, because in the initial part there will not be any data in our heap, so root will be pointing to a null value. Okay, so now what I'm going to do, I'm going to design my add function again. So let's say it is taking a parameter as a data. So this data needs to be added into our, it should be inserted into our heap, and our heap should be having the means it should conserve all the properties of that heap data structure. Let's say I'm trying to create a max heap. So the heap after insertion, the heap should after insertion also the heap should be having all the property of the heap data structure. Let's say I'm adding this data. So what I'm going to do first, I'm going to create a node. Let's say I'm naming it new node. Okay, I'm going to allocate memory to it, and I'm going to call my constructor that is of heap node, and I'm passing my data value to it. So what this constructor will do, what this line will do, this line will create a new node, and into its data part, the data will be stored. This data that is being passed to this constructor will be stored, and into its left and right and parent part, there will be null values stored. Okay, so what I'm going to do now, I'm going to check why new node is a pointer. Nan is asking why new node is a pointer. We generally do the things like this because we first create a pointer so that we can store that address of that pointer into a means because we generally use this only means we create a pointer and we allocate some memory to it so that the space that node should be it should be created. Okay, because it's a pointer so that in that let's say first a data, can we do it without pointer here? No, we cannot do it without the pointer because when we are doing it, let's say a node is being created because the structure, let's say the structure of our class looks like something this. It store a data part as well as it stores a pointer, means a pointer of right left node as well as a pointer of right node, means it stores a value so that for storing that value let's say I want to store this value, this should be a pointer that after if it is a pointer then I can store this value into here, let's say in the left part. If it is a pointer then only I can store the value into this part. Okay, pointer is just an address, we cannot do it without pointer. We've already did it in case of linked list, doubly linked list, and circular linked list. Okay, so let's move to our add function. What I'm going to do, I'm going to say that print an statement inserting that data slash n. Okay, so and again I'm going to check. Now I'm going to check if our root is equal to null. In that case, what it should do, it means that there is nothing in our heap. So what I'm going to do, I'm going to uh, save that value of new node into the root. Okay, now the root will be pointing to this new node, and what I'm going to do, I'm going to return from here, because if it's a root node its parent will be null, because it's our first node, its left child as well as its right child will be null. Okay, so now what I'm going to do, I'm going to check if it's not our root node. So what I need to do, I just need to, let's say if it's not our root node, okay, let's say 10 is being stored here and 20 is there and 30 is there. Okay, 20 cannot be here. Let's say 2 is here, it is 2. Let's take it 2, let's take it 9, and let's say 1 is here. Okay, let's say what I want to add into this, I want to add 11 into this heap. So where I'm going to add it, I'm going to add it into, first I'm going to add this node here, I'm going to add 11 here. Okay, although this is 2, this is not 20, so I'm going to add 11 here. So for adding 11 I should be having the address of this node. Okay, so how I'm going to calculate the address of this last node, which means this last parent where I can add my value. If this node is already filled, let's say here it is -1, let's say here it is 8. Okay, here it is 8, here it is 7. So if I want to add some node, so where I'm going to add it, I'm going to add it here. Okay, let's say I want to add 50, so I'm going to add first 50 here, then I'm going to call my Heapify function. So for adding something, I just need to know the address of that node. So for that, what I'm going to do, I'm going to create a function so that it should tell me that which one is the last parent, means which one is the last parent where I can add my value. So how I'm going to do that, I'm going to use a queue data structure here. So what our queue data structure will do, let's say I'm going to create a queue here, a queue of type node. Okay, so if you get this, you will in the coming sessions in the next week you are going to learn the level order traversal of a tree very easily. So please see this in a, it's a very important topic. So what I'm going to do, I'm going to create a queue of node type. So first I'm going to store my root node here. Let's say I'm not going to store the value. I'm going to store my node, so that if I want to try, means if I want to get the left child and the right child address of right child, I can get that. Okay. So what I'm going to do, I'm going to add 10 here, and what I'm asking, I'm going to run a while loop, and I'm saying please remove that value 10 here, and if its left child and right child exist, store this value into the queue again. Store these values. So 10's left child is 2, and the 10's right child is 9. Okay, the 10 is being deleted because it's a queue. And what I'm saying, again pop the front value, and if its left child as well as right child exist, store the values, store that nodes. Okay, not the values, store that nodes here. So 2's left child is 1 and 2's right child is -1. It is -1 here. Okay, let's say it is -1 here, and again I'm going to say 2 is being removed, so remove 9 as well, and if its left child as well as right child exist, store those values into that. Okay, store 8 and 7. So now what I'm saying, remove 1 here from here, and if its left child as well as right child exist, store that values. But one's left exists but one's right does not exist. So what I'm going to do, I'm going to break my while loop, and I'm going to see the address of, I'm going to return the address of this node. So what it means, the first node you found, means from, if you are traversing from the level order, let's say 10 2 9 1 -1 8 7, the first node you found, if its left child or right child does not exist, let's say if it's, let's say 50 was also not here, so the first node will be the one itself, because 10 2 2's both child exist, 9's both child exist, and once, although neither the left child or nor the right child exists. So what I'm going to say, I'm going to return the address of this node. I'm saying that this is the last parent. Okay, let's say the 50 exists here and 20 exists here again. So what I'm going to do, I'm going to store my 50 here, 50 and 20 here. Now 1 is being deleted, so now I'm going to remove -1 from here, and let's see whether -1's left or right exists. No, -1's neither left child exists nor right child exists. So what I'm going to do, I'm going to say that -1 is our last parent. Okay, is that the concept is clear with everyone? Please see the concept once. If it is not clear, please raise your queries. Okay, I'm waiting for your responses. Okay, Pratyaks is saying yes, it is clear. That's good. So what I'm going to do now, are we storing the address instead of values? Yes, Aryan, we are storing the address. We are going to create a queue of that heap node star. Smith is saying it is clear. That's good. So now what I'm going to do, so I'm going to design, let me quickly erase it. Let's quickly erase all this first. So what I'm going to do, I'm going to create a function. Let's say I'm naming it a last parent function. So what this last parent function will do, let's say what I'm going to do, I'm going to create a heap node here. Let's say I'm storing PAR parent LPAR. Let's say LPAR. Okay. So LPAR is equal to, let's say I'm creating a pointer last parent. Sorry, function last parent. This function will return the address of this last node. In this case, this one is our last node. So it is going to return the address of this pointer. Okay. Let's create our last parent function first. So our last parent function will look like heap node star, because it will return the address of heap type heap node star. So I'm going to uh, name its return type will be heap node star. So what I'm going to do, I'm going to create a function last parent. So I'm going to say that create a queue. I'm going to use STL in this case. Okay. What I'm saying, create a queue of heap node star. Let's name it queue. And I'm saying queue dot push, first push the root into this. Okay. Now I'm saying, let's say I'm creating a pointer, a temporary pointer, in which I'm going to store the pop values. Let's say I'm popping 10 from here, so I'm going to store the address of 10 here. So what I'm going to do, I'm going to create a while loop while queue is not empty. Sorry, empty. I'm going to use empty function. While queue is not empty, what you need to do, you just store into temp the value of queue dot front. Is that fine? The value of queue dot front. And what you need to do else, uh, in the temp store the queue dot front, as well as you remove that value from the queue as well, because let's say I'm storing this node, let's say in the extreme case, the root node is there, only root node is there. So if I'm storing this node address of this node into temp, and now what I'm going to do, I'm going to pop this value. Okay. Now I'm going to check and condition that if temps left, sorry, if temps left is not equal to null, either we can write only temps left. It means it is not equal to null. It means that if temps left exists, okay, either temps left is not equal to null or temps left is the same thing. And I'm going to say temps right. It means if temps left is not equal to null and temps right is not equal to null. So if both are not equal to null, so what I'm going to say, that please push both values in the queue. Temps left as well as push its right. Okay, temps right. Okay, if it is not the case, it means either temps left or temps right, either one of temps left or right or both is null. It means they both are not equal to, they both are not null. Means it means there is some value that is null, that is if either temps left or temps right or both is equal to null. So what I'm going to say, please break this loop here. So if the loop is been broken, so in the temp part that address will be stored. Let's say one comes, one's left as well as right part is null. So what in the temp will be stored, in the temp the address of one will be stored. So I'm going to say return temp here. Okay, is that clear? Our how our last parent function is look like, means why I've created this function. So it is going to tell us the address of that node, their last parent. Okay, now what I'm going to say, let's say I'm going to return in my heap, okay, in my add function. So in the LPAR, the address of parent will be stored. So what I'm going to check now, whether if the address of this is being written, let's say the address of one is being written here. So just let me use my pen. Okay, why this is not okay. So what I'm going to do, let's say if its left is if its left is having some value, let's say 14, although it's a max heap, it cannot have the value of 14. Let's say it was 16 here, so it can have the value 14 now. So what I'm going to say, here, if it's left is storing 40, in that case also the address of in the last parent function will return the address of this node. So how I'm going to check whether if it's the address that is being returned, either it's left is null or right is null. So I'm going to check whether if both if it's left and right both is null, so I'm going to store the value into the left part. So the first I'm going to check whether it's left is null or not. If LPAR's left is equal to null. Okay. So what I'm going to do in its case, so I'm going to say LPAR left part. Now its left part will be pointing to our new node because this is our new node, and this was the parent. So its left child will be this new node. And what I'm going to say store here, new node's parent will be this LPAR. Is that clear with everyone? And in the else part, if LPAR's left is not null, in that case this set of codes will be executed. So it means definitely its right part will be null. So what I'm going to say, LPAR's right, it is equal to new node. New nodes. Now new node's parent, again in that case also new node's parent will be LPAR. Okay. Now what I'm going to say, let's say this node is being added. Let's say I'm trying to add 14 here, and it is 16. So I'm going to call my Heapify function, and I'm going to means pass the address of this node. So what I'm going to do here, so let's say I'm going to create my Heapify function. I'm going to create my Heapify, let's say Heapify function, and I'm passing my address of this new node. That new node is being added. Okay. Let's quickly design our Heapify function. We have already discussed in the case of array. So I think the concept is already clear with you. So what I'm going to say, that void Heapify. Okay. I'm going to say that how my Heapify function will look like. It is going to check. Okay. Here some loop is null and null is true or false. Null and null is okay. You're saying null and null is true or false. Null and null. Okay, you're talking about in that case null and null. No, if it is null, the second case will not be checked. It will be always false. It will not be true. It will be false. But the first part, if the first part is null, the second part will not be checked because you are using double AND here. Then okay. So what I'm going to say, what I'm going to check here, in the Heapify function, I'm passing a node. Let's say a heap node. Let's say I'm naming it. Let's name it temp. Okay. What I'm going to say, if temps okay, let's say the node 14 is being passed here, so I'm going to compare it with its parent. So what I'm going to say, if temps parent data is less than, if temps parent's data is less than temps data. Is that clear why I'm writing this? If the parent is the data of the parent is less than this data of its child, so what I'm going to say, swap both values. Temps parent data as well as temps data. Swap both values and call my Heapify function again for the temps parent. because in that case also, if we have swapped 14 and 16, let's say in the case it was 1 only, so I'm going to swap 14 and 1, the 14 comes here. Now again I'm going to pass my this node with my up Heapify function, so the 14 is going to compare it with the value 20, or it's, let's say in this case it is 2. Okay, and now in the previous case, let's say I'm going to compare, let's say I've added 70 here, 70 is being greater than 16, so 70 will come here, 70 is greater than 2, 70 comes here, and it is greater than 10 also, so 70 will come here and 10 will come down. So now again it is going to compare it with its parent. So before doing that, I'm going to check whether if temp's parent, if the temp parent is equal to null. So in that case, you're not going to do anything, you just return from here. Is that fine now? Or do anybody is having any doubt in our Heapify function? So we have covered our add function. In the add function, we have used two functions, the up Heapify as well as our last parent function. Okay. How many of you have heard about the tree traversal? So how I'm going to check whether I have created the right heap or not? Is there anyone who is having problem with the traversal, the tree traversal? You know, any kind of traversal means how we can traverse our tree, either in order, pre-order. Okay, in order. Okay, Nani. Okay, Shrey. Okay, Nani Singh. No, I don't know. Shrey Singh. Yes, in order, post order. Yes. So I'm going to use my tree traversal so that I can get means we are getting the correct output or not. If you're not comfortable in the tree traversal, in the coming session in the next week, so we are going to completely discuss about the tree part. So in that case, we'll discuss the traversal in details. So now what I'm going to say, I'm going to quickly tell you about the only one traversal. Let's say I'm going to tell you about the Inorder Traversal only. Okay, what I'm going to do now, I'm going to quickly explain the concept of Inorder Traversal, so that if you're not comfortable with it, so how our Inorder Traversal looks like. Let's see. I hope most of you are already clear with that Inorder Traversal. Let's say it is having, I am doing it for the binary tree. Let's see, it is having one node, 5 here, 4 here, 6 here, let's say 3 here, because we are talking about the max heap. But this works in the case of any tree. Let's say 2 here and 1 here. So how our Inorder Traversal will look like? The Inorder Traversal looks like, the first we are going to print the left node, then I'm going to print this root node. After that, I'm going to print the right node. Okay. So let's say I'm passing this node to print the Inorder Traversal. So what it is going to print first, whether it is going to print its left part first, then it is going to print the 10, and after that it is going to print 4, means the right part, the right subtree. Again, the same conditions follows, the same rules follows for this condition as well. So if I'm trying to print this subtree, again the condition is same for that subtree. So what I'm going to say, that if I want to print this complete tree, what I'm going to print, I'm going to print 3, then I'm going to print 5, then I'm going to print 2. Let's say it is being called for this function. So its left side does not exist. So if its left does not exist, I'm going to print 3 first, and I'm going to print its right side. Its right side does not exist, so I'm not going to print anything. So this subtree is being completed. Again, after that, I'm going to print 5, and after that, I'm going to print its right side. If its right side's left does not exist, so I'm going to print this node 2. Its right also does not exist. I'm not going to print anything. So this right side is being, this part is being printed. After that, if I came here, so now the 10 is going to be printed. Okay. After that, the complete left part is over. Again, the node is being printed, the roots itself is being printed. Now I'm going to do the same for its right subtree. So in the right subtree, I'm going to first print its left part, then I'm going to print its node, then I'm going to print its right part. So in its left, again the condition follows the same. In this nodes, I'm going to first print its left, then I'm going to print its root node, then I'm going to print its right. Okay, its left does not exist, so I'm going to print its root node first. Its right also does not exist, so I'm going to say that I've completed already my task. Now you can move further. So this node left is being printed, so I'm going to print this root node, and after that I'm going to print its right node. Its right node does not exist, and I'll return to my root node. So although this was the right subtree, after that does not check this anything. So the first will be 3, 5, 2, 10, 1, and 4. This will be our in order traversal. So we have already created a tree. Now I'm not going to explain you the code of in order traversal, although it's a very simple code of recursion. If we still face any doubt in the code, we'll discuss that in the coming session of trees. Okay. Right now we are discussing about the heap. So I'm going to use that in order traversal. Let's say I'm creating a function here. Let's say void function, void print, and what I'm going to pass through this function. Okay, let's say I'm printing a statement here, printing the data of the heap. Okay, and what I'm going to say, I'm going to call my in order function. So what in order function do? In order. So I'm going to pass my root through it, not root, because root will be altered. What I'm going to say, I'm going to create a temporary node, heap node. In that part, the address of root will be stored. I'm saying that call in order function, in order. So I'm going to create an in order function. So this in order function will discuss it in that coming week as well. So if you are not comfortable with this function, do not worry about that. So what I'm going to do, I'm going to pass my root node through it, and I'm going to print an ENDL here. Okay. Let me quickly design my in order function. In order, let's see. Okay, this is our heap node. Let's say I'm calling it HE, and what I'm going to say that first call in order for HE is left. So I'm not doing anything. I'm saying that first solve the in order for HE is left, then print me that HE's value data, and I'm saying that call the in order for HE's right as well. Okay, but this is the simple function, and I'm going to create a base case. If HE is equal to null, what you need to do, you just do not need to do anything, you just return from here. Okay, let's quickly create an object for our heap class. Let's add some data. Let's see whether we are getting the correct output or not. Okay, so h.add, let's say I'm adding 50 here. Okay, 50 here, h.add, let's say 70 here, h.add, let's say 56 here, h.add 58 here, sorry, 58, h.add 89 here, h.add, let's say one more data, 46 here. Okay, so which one is the maximum value? 70 is the maximum value, so 70 should come means in between, so it should be a root of our tree. Okay, so what I'm going to do, I'm going to call my print function for it. Let's see, we have, okay, let's see, we have done everything right or not. everything is fine. Okay, so it is saying Q. Okay, we have not included our Q here because we are using iStream only. Let's type with slash so that does not create any problem with slash std c++.h. Okay, let's check. So what it is saying, q dot push root is not declared here. So in the line number 21, okay, the root is not declared here. Why it is saying the root is not declared here? So where is our, okay, I think it is out of the class. Okay, we have implemented this function out of the class, so it should be inside the class. Okay, let's quickly do this. Let's see whether everything is right or not. Okay, again, parent. We have missed the spelling of parent as well. Let's quickly do this. So where PARENT. Okay. Now I hope it should run fine. Let's see whether we have used semicolon or not. Okay. We've done everything right, I think so. So 50, 70, 56, 58. So it has all been added. 89 is the max value. So root is in heap mode. Yes, Nanny, thanks. So let's quickly create our heap tree and let's try to do it in order. Let's see whether we are getting the in order correct or not. Okay. Okay, let me quickly remove all these. Let's see our heap, how our heap should look like, and let's see it's in order whether both are the same or not. Let's see if 50 is being added. Let's say the 50 is here. Okay, I'm going to create quickly. I'm going to create a heap quickly. Okay, the 70 will be added first. It's left, and it will be swapped with the 50. Okay. I hope now you're all getting why it will be swapped with the 50. So the 50, the 70 comes here, and the 50 comes here. Okay. So again, I'm going to create. I'm going to add 56 here. So the 56 will be added, and we don't need to do anything because the 56 is less than the 70. And I'm going to add 58 here. So if the 58 is being added here, okay, the 58 will be being swapped with this value because this is the 50 is less than this value. So this will be 50. Okay, because 58 is less than 70, so I'm not going to swap it with its parent. Again, after 58, I'm going to add 89 here. Okay, so 89 will be swapped with the 58, and here also 89 will be swapped with the 70. So 70 comes down and 58 comes down. Okay, so I'm going to create quickly update both all the values. Sorry, it was 58. Okay, it was 58. So here comes 89. 70 comes here and 58 comes here. Yes, it is a heap mode. That means heap data structure. So 89 is being added, and I'm going to add 46 here. Okay. So let's quickly create our in-order traversal for this tree. So our heap will something look like this. Okay, and I'm going to write my in-order traversal. So this 50 will be printed first because the leftmost child will be printed first, then 70, then 58, then 89, then 56, then 46. So the first will be 50, 70, the in-order traversal. If you're not clear with the in-order traversal, it's okay. We'll discuss it in the coming session. 89 will be here. After that, the 46, because it's the left child of this right subtree. So the 46 and the 56. Okay, we are getting the same tree traversal because 50, 70, 58, 89, 46, and 56. Is that fine now? Or do anybody is having any doubt in this traversal? Let's try to add one more value. Let me add one more value. Let's add if I'm trying to add 9 here, so 9 will come here. So what output I should be getting? 50, 70, 58, 89, 46, 56 and 9. Okay, 9 should come in the Inorder Traversal at the last. Let's say I'm trying to add 9 here. Okay, I'm not use semicolon here. Okay, 9 is coming at the last. Is that clear with everyone? Means the concept. If it is clear, we can move to the deletion part. Okay, Nanny saying yes. Smith is saying yes, it is clear. That's good. Okay, saying all clear. That's good. So what I'm going to do now, I'm going to create my delete function, remove function. So void remove. Okay. For removing, I should be first checking whether is empty returns true or not. If it's empty returns true, it means our heap is empty. So I'm going to print a statement cout heap is empty, and I'm going to return from here. Let's quickly design our is empty function. Bool is empty. What will be the condition for empty? If root equals to null, it means our heap is empty. So it should return true here. I think we have already discussed all these things. So I'm doing it quickly. So return false here. Okay. Up to here it is clear, I think so. If our heap is empty, what our remove function is going to do? This is empty function will return true, and it is going to say that heap is empty, and it will be returning from here. If it is not true, means if our heap is not empty, so what in this case what I'm going to do, I'm going to first print a statement that deleting last data. No, it will be roots data, because in the heap case we always delete. Let's say if I'm calling this function remove function for this case, so in this case 89 is 89 is going to delete first. So the 89 is presented root, so I'm going to print a statement deleting ends data. Okay, it will be endl. Let me quickly erase this. Okay. So now let's see endl, and now what I'm going to do for deleting, we have already discussed in the previous session what I do in the case of deletion. So first what I do first, I swap the root node. First I swap the root node with the last node that is being added into a, means with which, that is which one is the last node. This in this case the 46 is the last node. Okay, so in the label order traversal we can say that the node that comes at the last, we are going to swap it with the 89, with the 89. Okay, with the last value. So what label order traversal is? Label order traversal, we print this data in the label order: 89, 70, 56, 50, 48, 46. Okay, we'll discuss it in the pre session as well. So now what I'm going to do, I'm going to first check that which one is our last node. So for that, again I'm going to create a function. Let's say I'm going to call it my last node function. So this will return, let's say in the heap node, let's say I'm creating a temp here. I'm not creating temp here. No? Okay, let's say I'm going to, okay, not temp, let's say I'm going to name it last, because it will be our last node into our heap data structure in the label order traversal. Okay, so now what I'm going to do, I'm going to say that return the value of that node. So for that I'm going to create a function last node. Okay, so this function will return the address of this last node. So let's quickly design first this last node function. void, sorry, it will not be a void type because it should have it will return an address. So what I'm going to say, its return type will be heap node star. So last node, let's say I'm naming it last node, and sorry, it will not pass any argument through it. Again, what I'm going to do, I'm going to use a queue data structure for that. So how I'll get this last node, let me quickly explain you. So let's say I'm going to create a queue here. Okay, so now what I'm going to do, that I'm going to add the root node here. The 89 will be added here. The node will be added, not the values. Okay, so I'm going to add 89 here, and again I'm going to call a while loop while my queue is not empty. Do this operation. So remove 89 and store its child to queue 70 and 56. This time do not check the conditions. First just check if it's any of its child exists. Please and push it into the queue. So 70 and 56, sorry, it will be 56. So the 56 is being added. Now I'm saying remove 70 and add 70 child, 50 and 48 here. Sorry, it will be 58. Okay, and again what you need to do, remove 56 here, and if it's any of its child exists, please do push it into the queue. 56, 46, the 46 comes here, and again remove that 50. It's left or right child does not exist, do not add anything. Delete 58, its left and right does not exist. Delete 46, and if it's left and right does not exist, so do not do anything. So the node that is being deleted in the last, that is going to be a last node in this case, because what I'm going to do, I'm going to add 89 and I'm going to add it's both of its child and going to delete 89. So again the 70 is being deleted, that's 50 and 58 will be added, the 46 will be deleted, the 56 will be deleted, the 46 will be added, the 58 will be deleted, and then the last the 56 comes here. Okay, is that clear? So what I'm going to do, I'm going to create a queue again, queue of again heap node type star. Let's say I'm naming it queue again, queue dot push root into it. Okay, and while queue is not empty, queue is not empty, sorry, empty, while queue is not empty, do these operations again. Let me create a pointer here first so that I can store that the address of that last node that is being deleted. Let's see, I'm saying it last here. Okay, in the last I'm going to store that queue dot front. Okay, I'm going to say delete that, sorry, delete that front value from pop that value from queue. Okay, and I'm saying if last left exists, if it's left exists, what you need to do, you just push that into that queue. Push last left. Okay. I'm again saying if last right exists, last right exists, push that into the queue. Okay, so while loop completed here. So when while loop will be broken, the queue, when the queue is empty, and when the queue is empty, the last node that will be popped, the queue dot front, that in that case it was 46. Okay, So I'm going to return the address of that last node. Is that clear? The last node function. Okay. So where is our okay, our remove function is here. So now what I'm going to do, if we have found our last node, so I'm going to swap both values with the root node. Okay. So I'm going to say swap roots data with the last data. Okay. But before doing this, check this also. If roots, okay, sorry, yes, okay, check whether our last node, if the last node is the root itself, because if there is only one node, what our last node function will return. Let's say if there is only 89 node 89 is there, and its left and right child does not exist, so what it is going to return, our last node function will return the address of 89. Let's check if that last is equal to root. Okay, if the last is equal to root, if the root is the last node itself, so what you need to do, you just delete, sorry, delete that node, because if there is only one node, you don't need to swap it with anything. Just remove that node. So remove that last node, and what you need to do, root is equal to null here, because if there is nothing, root should be pointing to null. Okay, and return from here. If last is not equal to root, then swap the values roots data and the last data. Okay, now what I'm going to do, let's say 89 will be swapped with the 46. So what I'm going to do now, let's say I'm going to swap it first. So the 89 comes down and the 46 goes up. Okay, the 46 will come here, the 89 is comes here. Okay, you are saying 151 line. Okay, I have not added semicolon, I'll add that. Okay, 89 comes here, so our last node is pointing to this node now. And what we do after swapping both values, I delete this node. Okay, so for deleting this node, its parent means its parent's left child should be pointing to now null, because if I'm deleting this node, its parent 56 left should point to now null. Okay, so what I'm going to do, I'm going to add semicolon here first, and now what I'm going to do, if, sorry, not if, what I'm going to do, I'm going to check whether means what is the parent of that last node. Let's say heap node, sorry, heap node par, let's say pr equals to the last node's parent. Okay, so again, if 89's, we got the 89's parent 56. Right now I means at this point I don't know means the 56 left child is 89 or its right child is 89. So first I'm going to check whether if that prs, if its left child is null, means if its left child is 89, so I'm going to make pr's left null. Let's say if pr's left is equal to last, if its left is last, so what I'm going to do now, I'm going to make pr's left, sorry, first I'm going to delete that last node. Okay, and I'm going to do pr's left equal to null. Okay, if it's not, if it was not its left side, definitely it would be its right side. So I'm not going to check the condition, right? Directly I'm going to do delete last, and pr's left should be, sorry, pr's right should be null. Is that fine now? or do anybody is having any problem in this? So now I'm going to create my down heapify function because the 40, let's say that 89 node is being deleted. This node is being deleted here. Okay, this node is being deleted. Let me remove this node. The 49 is the root node now. So what I'm going to do, I'm going to call my down heapify function with the help of this root node. Okay, because it should compare with its both of its side, whether which one of its side is having the greater value. It should be swapping with that value. Okay, because in this case the 70 should come up and 46 should come down. After that 46 should come down here and 58 should come up here. Okay, so now what I'm going to do, I'm going to design my down heapify function that in the case of array as well, we have discussed this function already. So in the down heap function, I'm going to call a parameter. I'm going to tell a parameter that down heapify is root, means from the root down heapify. Okay, so let me quickly design my down heapify function. Sorry, where is my down? Okay, down heapify function, and let's say heap node. The parameter that is coming, I'm taking is, let's say, heap or he. Let's say he. So now what I'm going to say, as we have already discussed in the case of array, when the same concept I'm going to use here. First, I'm going to create heap node. Let's say largest. In the first case, I'm going to store in the largest the he itself, the root itself. And now what I'm saying, that if he's data is less than if he is left. So first I'm going to check if he is left. Let's say he is right now this. If he is left data is greater than the largest data, because in the first case the largest is the he itself. Okay. So what you need to do, you just update the largest with the he is left. Left. Okay. If I'm going to check it for that for the right as well. If he is right, right data is greater than the largest data, the data present at the largest. This concept we have already discussed in the case of array. Again, I'm going to repeat it here. H is right. So what I'm doing here, so in the first case, let's say 46 is here. So in the largest, I'm going to store the address of 46. And what I'm checking here, if H is left data, that is 70, is greater than H is data, because the largest is right now pointing to 46. Yes, it is greater than, because 70 is greater than 46. So what I'm saying, in the largest, store the address of H is left. Again, what I'm saying, if H is right now pointing to this. If H is right, that is 56. If it is greater than the largest data, right now largest is this node. So if the 56 is greater than 70, now update this largest. So 56 is not greater than 70, so it is not going to do anything. Okay. Now I'm going to check if the largest is the same or not. If largest is not equal to he, that means either of its child means it's greater than the he itself. So that value is stored in the largest. Let's say it was 80 here. So largest as well as he will be pointing to the same node. So this condition will not satisfy here. Okay. So right now I'm creating if largest is not equal to he. So what I'm going to do in that case, I'm going to swap both values. The largest data as well as he's data. Again, I'm going to call my down heapify function for that largest. Because let's say in this case 46 and 70 will be swapped here. The largest will be pointing to now 46, because 46 comes here, because largest was pointing to a node, not a value. So largest is still pointing to this node, and I'm going to say that call a down heapify function for this node as well. So now the 46 comes here, and it will be called, the down heapify function will be called for this as well. Okay. And before doing HE's left, first check whether HE's left exists or not. So HE's left and add HE's right HT and add. Check whether HE's left or right exists or not. Otherwise, we'll get a runtime error. Let's see whether we are getting, okay, we have not called our remove function. Okay, let's call a remove function first. Let's say, okay, we have not added the 9. Okay, let's add 9. Will not be any problem. H dot remove. Which value should be removed? The highest value, that is 89. Let's see whether 89 is being deleted or not. See whether, okay, 89 is being deleted. Yes, the root node is 70 because we have already discussed why it will be 70. Let me quickly write itself. Means the 9 was there also. The Inorder Traversal was 50 because it was 50. I had removed this. Okay. So 50, 70, it was the Inorder Traversal in the first case. So 89 is being swapped with, 89 is going to swap it with 9, not with the 46 in this case. Okay. Because let me quickly write this first. In this case, it was 89 here. Okay. Okay, 9 will not be here. The 46 was here, I think so. Yes, no? The 46 was here and the 9 is here. Okay. Is that fine? And 89 was here. So now the last node is 9, not the 46. So it is going to swap it with the 9 itself. So 89 will be, 89 will come here and the 9 goes here. Okay. This node will be deleted. And now this root for the down heapify function will be called for this node. So it is going to check whether which one is the maximum value. So the 70 is the maximum from both of its side. So it is going to update that both value, means swap both values. So 9 comes here and 70 comes here. Again, it is going to check whether, again it is going to call the down heapify function for this. So it is going to check whether which one is the highest value. So 58 is the highest value from both of its sides. So again it is going to swap both values. So 9 will come down and 58 will come up. So 59, 58, it was 58 I think so. Yes, 58 comes here and 9 comes here. Let's quickly draw a Inorder Traversal for this. Write an Inorder Traversal. It will be 58, 9, and after that 70 and 46, 46 and 56. Okay. Sorry, it was 9 here. So what I'm going to write, 50, 58, 9, 70, 46, 50. Sorry, 56. Let's see whether we are getting the same output or not. Let's match it with the output 50, 58, 9, 70, 46, 56. Yes, we are getting the correct output. Is that clear with everyone? Let me quickly call our remove function one or two more time. So this time 70 should be removed because 70 is the root node. Okay. So 70 is being deleted. That's good. Let's call this function two more time. So after 70, which one is the highest value? The 58 is the highest value, so 58 should be deleted. After 58, the 50 should be deleted. Okay. Okay, 89, 70, 58, then 56. Okay, 56 was also there, so 56 is being deleted. So our root node, so our heap is right now 46, 50, and 9. So 50 is the root node, 46 is the left side, and 9 is the right side. Is that clear now, or do anybody is having any doubt still? Let me quickly call my function 3 times more. Let's see. Okay, 89, 70, 58, 56, 50, 46, 9. I think we have already discussed about the heap sort, because this in the max heap we are getting the descending array, but in the case of min heap we'll get the ascending order of our data. Let's say I'm going to try to delete one more time. So in this time I should be getting a statement that heap is empty. Okay, we are getting a statement heap is empty and printing the data of the heap. There is